Hello, everyone. Welcome to today's Lunch and Learn on building a video semantic search engine with 12 Labs and ApertureDB. We're going to give everyone a few minutes to join. So while we're waiting for everyone to join, if you can please, I'd love to know where you're joining from. I'm located in the San Francisco Bay Area. So if you can put in the chat where you're joining from, that would be great. Awesome. I see that I see we've got the San Francisco Bay Area. Anybody else would like to hop in? Oh, awesome. We have Seattle. Great. Okay. So without further ado, we're going to go ahead and get started. Once again, welcome to today's Lunch and Learn, building a video semantic search engine with 12 Labs and ApertureDB. My name is Deniece Moxy, and I will be your host. My name is Deniece Moxy. I am the Director of Product Marketing at ApertureData, and I'll be your host for today's event. Before we get started, we have some housekeeping details. Recordings of the Lunch and Learn will be available on demand after the session. You may post your questions in the chat window, and we will answer them at the end of the Lunch and Learn. And if we do not have time to get to all your questions, we will send a follow-up via email with the on-demand viewing instructions. And finally, links to some of our resources that are viewed in this Lunch and Learn will be provided. So without further ado, we'd like to go ahead and get started with our Lunch and Learn. Videos are everywhere. They're in our feeds, cities, and even shaping how we experience the world, from enhancing public safety to improving traffic flow and customer experiences. Video data holds a wealth of insights, but turning raw footage into actionable business outcome, that's a challenge. In today's Lunch and Learn, we'll explore how two innovative technologies from 12 Labs and ApertureData work together to help you unlock the full potential of your video data and drive smarter business insights. Our presenters today are James Lee and Gautam Saluja. James Lee is the head of developer experience at 12 Labs and is a leader in developing video foundation models for real-world applications. Most recently, he coordinated an inaugural workshop on video language models at Near IPS in Vancouver. Also joining us as a presenter today is Gautam Saluja, senior software developer at ApertureData, who brings extensive experience in Unix-based systems, Linux interval, and network communication. His passion for working with companies like 12 Labs to integrate technology such as ApertureDB to build real-world applications. Without further ado, I'll now turn it over to James, who will begin the webinar.
Hey guys, thanks Deniece for the introduction. Really appreciate the opportunities to, represent 12 Labs and collaborate with ApertureData team over the past year or so. So yeah, let me start sharing my screen and talk a bit more about our recent work on multimodal embeddings. Great. So yeah, I hope you all can see my screen. So this presentation is created jointly with my colleague Manish, who's the product manager focusing on the Embed API product, which we'll discuss in details. And this is the quick agenda of a couple of my slides. So quick overviews about the concept of embeddings, from unimodal embeddings to multimodal embeddings, talking about some of the use cases, talking about the 12 Labs platform, how the embed API fit into it. And then in the later half of the session, me and Gautam will talk about the demo application build between our API and Aperture, which is the multimodal vector DB in this case. So just a quick slide on the concept of embeddings. So an embedding is a mathematical representation of a set of data points in a lower dimensional space, can capture the underlying relationships and patterns. And embeddings are often used to represent like complex data types, right? Beyond the tables, structured data in the over things like images, text, or audio in a way that, foundation models, large model can easily process. So, for example, in this image, the axis denotes the features that could have been learned by the embedding. As you can see, the concept of cat and the concept of the dog vectors can lie in both the legs and breadth hyperplane, whereas the human word vector representation lies in the hyperplane of those three features. So that's how like models see, different concepts. They have a lot of dimensionality in the way they see the world, and then it can break down this concept and try to fit that concept into a specific real estate within that world. Um, so basically we have unimodal embeddings, things like image, text, or audio, right? Um, and basically those embeddings like convert those corresponding data type into the corresponding vectors. At 12 Labs, we focus really on video embeddings, and these video embeddings are basically the numerical representation of videos in low dimensional vector space, where each video can be represented as a numerical vector. And the idea is that these video embeddings can capture the semantic meaning and visual features of those videos. And the popularity of video embeddings can be attributed to the multimodal evolution of vector embeddings. So as I explained before, right, like with unimodal embeddings, you can only represent that concept. But if you think about video as a modality, video consists of visual information, sound, speech in the audio aspect in the video. Sometimes they also have text on screen as well, right? So you need to combine all these modalities together, to get a holistic understanding of what it makes a video, right? Yeah, so that's we build a video transformer architecture model called Marengo, which I will explain in the next slide, that basically generate multimodal embeddings from video. Go back to previous slide. Yeah, so this is a quick slide on architecture Marengo 2.7, which we released in December. And it's a transformer-based architecture that can process video content through a single unified framework. It can understand the visual elements. So think about like fine-grained object detection, motion dynamics, temporal relationships, as well as appearance features. It can also capture the audio elements, things like native speech understanding, non-verbal sound recognition, and music interpretation. And the core element of Marengo 2.7 is what we call a multi-vector representation approach. So in the previous version of this model, we call Marengo 2.6, we basically try to capture everything into a single embeddings. However, with Marengo 2.7, we try to decompose the raw input into multiple specialized vectors. So you can see on the right side, each of those vectors can independently capture the distinct aspect of the video content, right? From visual appearance and motion dynamics to things like OCR text and speech pattern. And the fact that we make it more granular enable the model to get a more nuanced and accurate multimodal search capabilities, right? And this is really important for tasks like detecting small objects while also maintaining a very good performance in general, like text-based visual search. And just to illustrate, right, like here is an example where you fit in the text crowd of a man with a horse, you fit in an image of a horse, you fit in an audio sound of a horse making noise. Then Marengo will basically decompose the modalities into corresponding encoders and generate the embeddings, right, from the encoders. So the implication here is that you can perform any 20 retrieval activities, right? So you can perform things like text to audio search. You can also do things like image to video search, even things like text to image search and like audio to text search. So that open up a lot of flexibility in terms of the application that you can build. Just some note on the performance of the model for the folks who are interested on the research side. We have a whole blog post talking about it. And our research team basically evaluated 2.7 on more than 60 benchmark dataset that cover a wide range of tasks from text to visual, image to visual, to text to audio search capabilities. Very comprehensive assessment of what it means for a model to have multimodal understanding. And then other very brief conclusion is like the model demonstrates state-of-the-art performance across all these benchmark, specifically with remarkable achievements in image to visual search capabilities. Meaning that like if you feed in, if the video have like small objects and small image objects logos, then the model can detect extremely well. So that's a bit on the model side, but like since this webinar is with Aperture, and our core audience here is the developer, right? So we also abstract our model into API. It's a high-level diagram illustrate the architecture of our platform and how everything interact together. The embed API part you can see sit on the right side there, where you generate raw embeddings once you feed in the video, right? And so that's on the Twelve Labs platform, but this is another diagram I create to showcase how it might fit into a vector database. So the top diagram is basically like similar to the previous platform, right? Architecture, where you throw in your input and you use our embed API to get the embeddings as well as associate metadata, and you're going to store those embeddings in a vector store such as Aperture. And you can perform a lot of interesting downstream application. For example, we'll talk about retrieval augmented generation quite a bit, where you can have another like multimodal LLM that to generate text embeddings and have a conversation, right, above the video, because those text embeddings will basically talk directly with the multimodal embeddings that has already been stored in Aperture data, right? So that's pretty cool, right? Because if you think about it, you can try out different multimodal LLMs. You can do things like generating different text query about the video itself, open up a lot of interesting use cases. This table provides some details about the specific metrics about embed API, as I explained before, all in the same data space. And for search, for retrieval activities, we use cosine similarities to perform to measure relationships between different modalities. And then the embedding dimensions are 1024. This slide talk about the stack of how we think about it fits into the end-to-end, video and enable application. So we build the model under the hood, we expose them as API, and then those APIs will enable different, upstream application, right? From search to curation to recommendation, and then all the way to the top are the end user application that gonna interact with those application, right? Whether it's in education or media or security and healthcare. One quick slide on some of the use cases, right? And this touch on the second green horizontal part that I mentioned here. So hybrid search, so you can combine semantic search with keyword search. Recommendation system, so you can use video embeddings to perform video to video search for better recommendation of video content. RAG, retrieval augmented generation, I already talked about the previous slide. Basically, get high quality text output from video. And finally, data annotation. So traditionally, like, to perform data labeling, you have to manually collect those sample videos and like manually label them, right? But you can do things like embeddings, visualization, data curation, in order to quickly figure out what video to label, right? Significantly reduce time it takes to, classify and detect anomaly in the video content. So a couple of resources that Deniece will be sure to show to the audience later on. But we have API docs, we have cookbook, sample application built with Twelve Labs Embed API, and then most importantly for this webinar is the blog that we've been written with the Aperture team, collaborating with Gautam and Vishaka, where we showcase how to build a semantic search engine between our two products. And we'll talk more. We'll go over the code in a little bit. And yeah, so this is the one quick code reaction is I'm also have a Discord channel for Twelve Labs where a lot of folks gonna join and talk about the experience building video application. So good luck for you to join and connect with other folks who are interested in multimodal AI. So yeah, I will stop my screen and pass it into, I guess, back to Deniece.
Thank you so much, James, for that wonderful overview for 12 Labs and the project. Next, we have Gautam, Senior Software Developer from ApertureData, who will present an overview of ApertureData, as well as talk a little bit about the project before diving into the collab notebook where you can actually see the product in action.
Hi. Thanks, Deniece, and everybody, welcome. Deniece, I have a lingering question because of your opening remark in this presentation. You said where all people are joining from, and it seems like most of the people are joining from the west side of the country, and which led me to think that why is this called lunch and learn? I mean, it should be breakfast with learn or something like that, right? Unless you want people to watch it recorded 3 hours later along with their lunch. Anyways, jokes apart, I'm going to talk about this semantic search that we thought of building alongside uh, 12 Labs model for searching from anything, like any modality into video. The reason why that uh, API particularly appealed to me was because ApertureData itself uh, is something of like a multimodal store of all the visual data. That's what it's primarily focused on, and it's also a vector store. So uh, basically, I would think it's a very good fit or a complement for that model because it can house all the stuff uh, that Marengo can ingest or can transcribe into embeddings, and then it can even store each of those things in a connected graph. Uh, so let's get into the weeds of how things go. I'm going to give a brief overview about the capabilities of Aperture Data for a couple of slides, and then we'll dive right into the applications design. So, okay. So this is the overview of what ApertureDB is. It's a database, but it's a very different database as compared to a lot of offerings out there. You can put your images, videos, audios, even embeddings and other binary information apart from the text and a structured formatted things like JSON and such. Uh, it all goes in ApertureDB, and it can be laid out in a connected manner, like the relations and the connections are up to the users to define, and then it can tie into the entire pipeline for a machine learning application, including labeling, curation, what have you, training, and of course querying. Uh, Now, before we get into the application, a little bit about some cursory benchmarks we have recently performed, and alongside our current the popular cloud vector DB providers, and for a relative configuration, for a comparable configuration in each of these clouds, we have found out that ApertureDB does offer a good value for money in terms of the speed, the capacity, and uh, both in terms of throughput and latency. Uh, of course, if the need of the data storage gets a little higher, then we have like enterprise solutions as well, and we have like tested our scaling, our vertical scaling with uh, billions of entries on the graph, and we have also ascertained that our reads can be read throughput can be increased significantly by horizontal scaling. So we grow as in how the user's requirements are. That being said, let's get to the interesting part. But before we move there, the interesting thing here would be, these numbers can be verified easily if there's a developer, like a person who's trying to tinker around with DBs. You shouldn't take our word for this. You can sign up for Cloud Easy and you get a free trial instance and you can vet these claims out. All right, now the fun part. We are going to build an application which is going to be searching semantically through a video, and uh, is going to take in an input video, and there's the key points that this application is going to service. Basically, we have a video in hand. It's for this particular example and this webinar's scenario, we have taken a 4-minute video, but we are interested to just get to the interesting points on that video. And one of the possibilities of doing that search is by providing a textual prompt to what we're looking for. And the other modality that we can exploit is to have an image which is very similar to the frame or the video that we are looking into. And we want to just get into that region of interest. When I say region of interest, I mean temporarily in the video. So we don't have to seek through the tons of footage. Usually cameras are notorious for generating. So I'm just going to play this video and scroll through it to some of the interesting positions here. And I'm not going to make everybody see a 4-minute video when I couldn't. So here's a query for which here's a sort of like a section for which we have an interesting query. And as you can see, the screen has a bunch of outfits here. Then we scrub a little further. We have another screen around this point where we have a water body here. It's blue in color, and you can see it had a very specific appearance of like a beach to it. Let's go to the next. Before even diving into the notebook, I just want to give a very high level gotchas here. We might have a vocabulary difference between what would there be in some slides and the APIs. Just the key thing to keep in mind is embedding in ApertureDB nomenclature is known as descriptor. It is also generally known as vectors, feature vectors, and they are all one and the same thing in the subsequent slides. The other thing to keep in mind is a segment from 12 Labs API is a region of interest from a video, which means that it's a part of the video, a snippet, a portion. It has a starting point and an ending point in terms of timestamp, and ApertureDB calls it clip. That should be all to keep things in context. Now, ApertureDB lets you model these objects, the variety of objects in a connected way in a graph. And for our application, we'll take an input video and we'll persist it inside the ApertureDB. Alongside it, we'll connect the clips that get generated through a call to the Marengo 2.7, and even the embeddings that get generated from that model. So we will keep things in context by hooking them up like this, and then when we look for some similar descriptors or embeddings from the KNN search, we can easily get to their connected relevant multimodal data. The application itself will have two phases, two legs to it. One is it's going to be writing all the information. The raw video itself goes directly into the DB, and it also goes through a pass in Marengo where it gets the segments and the corresponding embeddings, which leads to that diagram we just saw. And then there would be the search, where, as James had earlier told, that Marengo can take any form of input, any modality of input, and convert it into embedding that exists in the same latent space as that of the video. So a prompt would lead it to generating embedding, and we would use that embedding to do a lookup, a KNN lookup. And because ApertureDB has a connected graph concept, we don't need to go to any other system or have a API tool, which is usually probably in a bucket or a file system, to retrieve the binary objects. It will be all there in ApertureDB, and we will soon see this in action, how concise it makes the code do. Similarly for image search, and again, Marengo is the model that talks in all the modalities. ApertureDB is something that stores all the modalities, and here we have the application. Very simple and clean. Here are some resources which would be shared by Deniece at the end, but for now, let's get to looking at some code. And I'm going to open the notebook here, and James is going to start off the explanation. I'll follow. There you go, James.
Yep, we got it. Yeah, hope you can hear me. So yeah, this notebook is demonstration of a workflow between 12 Labs API and Aperture. And I think the motivation here is that if you follow this workflow, folks like developers, data scientists, for instance, right, can learn how to leverage our API to create rich, multiple embeddings and seamlessly integrate them alongside the source video into ApertureDB to perform things like semantic retrieval, right? And I think some of the use cases that we can talk about here is around like sophisticated video understanding and retrieval system, things like recommendation, content discovery, etc. So the first part here is setup and installation, right? So we will need to install the necessary libraries and dependencies that require to work with 12 Labs and Aperture. The nice thing is we both have Python SDK, so you can simply do a pip install call. So in this scenario, pip install 12 Labs, pip install ApertureDB, all right? That will allow you to interact with those two SDK. After running those code, you should have the libraries installed and ready to use in the subsequent step of the notebook. So you import 12 Labs as a such function in the second cell right there. The next step is around API key configuration. So now you want to set up the necessary API keys from both product. And Colab, pretty cool ability for you to like securely store and retrieve the keys. So in this scenario, we store the 12 Lab T_API_key variables and ADB_password variable into a secret folder managed by Colab, and we just like call user.data.get function to retrieve those keys on the backend of Colab. Yeah, after that, you should be able to configure the credentials and get those variables set up. In this section now, we want to start generate video embeddings with our Embed API. So this code here, I can explain quickly what each of the function does. So we first initialize the 12 Labs client, right, with the API key. That's first code right there. Now I create a function called generate_embeddings, to create an embedding task using the Marengo 2.7 engine, right? And the input parameter is video URL. So you basically can put in a publicly available video URL as a parameter. And within that function, we create an embedding task to basically you leverage the SDK to code the embedding task, and then we monitor the task progress with the callback function and then wait for it to complete. And then once the task is done, we're gonna retrieve the results and extract the embeddings. So yeah, that task result parameter, key variable is basically the results that I mentioned that contain information about embeddings. So the embedding could be returned along with metadata, such as time range that they correspond to the time scope, right? So we already run this, and you can see the status change from processing to ready, and embedding test is done. And the return, the test result variable, right? When it return, you can see there's associate task ID, there's things like start time, end time for each embeddings, and the raw embedding itself, right? So embeddings underscore float, that whole array are the embeddings being returned. Yeah, so that's the code, and by using the API now you can easily create contextual understanding of the video. And the next step now is how we're going to work with those embeddings, right? So I pass it back to Gautam, so you can talk about the next phase of inserting the embeddings being generated into the database.
Thanks, James. I should point out that configuring the API key of 12 Labs and the ApertureDB password can be very easily done by going to this dashboard. I mean, once you sign up for the account for the 12 Labs platform, it's very simple. You click on the top right and you get to the API key you need there. Similarly, cloud sign up for ApertureDB lets you create an instance over there, and you can go to the cloud link, and all these resources are of course going to be sent to you post the webinar completion, but I'm just calling it out so that we are following along. And now that we have embeddings generated through the Marengo model, we continue with our semantic search idea. So we are going to talk about the data model. In my deck, I showed a presentation of how this data is going to be laid out in the DB, and ApertureDB's SDK allows you to define custom pydantic style objects, which can be used to generate the query in an implicit manner without needing to know the query itself. And these are the two models that totally define our tree that we had. Like, it was video to multiple clips and each clip to a embedding. And this is the top level element over there. It's a video to clips model. It has it's based out of a video model, which we understand, like ApertureDB understands natively. So we also annotated with the few properties over here: title, description, and clips. Clips would be something that we are going to connect our video to. A clip is nothing but a list of clip embedding models, which is a class derived out of clip data model. Now, clip data model is again going to have a link to a base model called descriptor model, which is a convenient class for specifying a vector and putting it in the DB. So that's the understanding of the data model that we have. Now we start with the video URL, the same one which we passed to Marengo to generate segments and the corresponding embeddings there. And from the task result, we have access to those the segments that it generated. So we create a ApertureDB client like this with the API, and this is a function that populates our data model with the response with this task result from the model. We just iterate over those clips, and as we saw earlier, they had start time, end time, and a embedding float over there. We are just going to convert it into our data model, which is the video clips model, and then we just return it back through this helper function. We create this video clips model, we put the clips in it, and each clip also has a embedding alongside. So once we make this connected object, all we got to do is generate a query for it, and first we also need to create a descriptor set, and a descriptor set is something like a collection or an index in the popular terminology or the common in different vector DBs, it might be even referred to as catalog or things, but it's essentially a descriptor set here. We generate a descriptor set to store this embeddings. We call the descriptor set Marengo 27, but you can be creative. My naming might not be the most fun. Then with this video object that we return from this function, we generate we have a helper function to travel this tree and make a query. We don't need to understand the query language at this point of time, but we can use that query, and we can execute the query against the DB. I have already run this code, and I did not get an error. Results is equal to 0 says that the query completed successfully. So I ended up adding the video and its connected clip, and the clip connected to the descriptor in this one shot. Now that the DB has that kind of a structure of the graph, it's time to look up in the second leg of things. We were going to do two types of searches, one with the text input and one with the image input. So here we are, and this is the fun thing. Again, we have this client right here, and we have this call to generate a text embedding. Instead of the task create, we are calling a API called embed create. We specify the model over here, and this is the text that is going to be this is the prompt that's going to be fed in to generate the embedding in the same latent space as that video. So it asks, show me the part which has a lot of outfits being displayed, and the embedding gets created, and sure enough, we can access this embedding from that segment. Towards the database side, we have a helper where we can create an object called descriptors, and it has a function called find similar. The find similar takes this input as it is, like the array of the floats, and again, we have some more helper functions to traverse the graph easily. So it says that, okay, you have the descriptors, but give me the clips type objects which are connected to it. And then we just iterate, we get those clips, we iterate over them. And this is a little bit interesting thing we do also here, just because the space is restricted and this was a very high definition video. We on the fly, before we tell the server to, even before sending us the response, to reduce it to 640 by 480, and let's see the outcomes. So for this prompt, show me the clothes, show me the part which has a lot of outfits being displayed, we get 3 matching clips or segments with their timestamps and their end times and the start times. And if we were to actually watch that clip, it's a 6-second video, which is looking very relevant, because in most of the video there is a person talking, and these are like the oasis in the desert, or needles in the haystack. So I get these top results, which are at different times intervals. Like first one we saw had 106 as a start timestamp and 112 as the end time. The next one again has one from the interval from 1 to 106, and yes, this is also not as full with outfits, but still it has outfits. It's got a different time range. I guess it was the best possible match after those top 2, and we have them in order of descending similarity. So that was how we use the text prompt to get to the relevant points of the video without scrubbing through the entire footage. We could have done it we could easily extend it to add multiple videos and then find out the video of interest based on what we are looking for. So that was our search by text example. I also took in I just grabbed the frame and cut and clipped the part of the video that I want to find, which looks very similar to this image. So this image is I call it beach, but it's not really a beach. It's more like a pier or something. Um, I'm just going to display this image here to just to see that what it looks like. It's it's uh, it's mostly blue with a blue sky and a bit of ground here. It's got this phone thing, right? Uh, uh, and some messages, I guess, or some keywords here. I'm going to search. I'm going to generate another embedding, but this time I'm going to say image URL instead of the text. It's much the same from 12 Labs, but it takes the input of image and then we have this embedding it generates. Uh, this time it comes inside a field which is called image embedding as opposed to the text embedding earlier. So we do a lookup on in a collection in the database uh, with the image embedding there, and we just run this, and this is the clip. I mean, the 6-second segment that it looks up. So you can see, because of course it was a frame from the same video, it is the clip which uh, very closely resembles our input. Of course, there are these bags popping up, but it's video versus image. So yeah, these are the two types of searches that I would like to show. Uh, 12 Labs also has a way to generate audio embeddings to look up inside a video. And that could be a good exercise for anybody who's interested to try out and build their application. That's pretty much it for the application. I hope you liked the idea, and maybe James, do you have anything to add here? I'm done.
Yeah, awesome. Thanks, Gautam. Yeah, no, I think this is just the initial step of our demonstration workflow. But as he explained, you can do audio search. I think hybrid search is another one that you can also explore. So leveraging both semantic embeddings, but also keyword search right together to make your retrieval become more powerful. Yeah, I think that's pretty much it. Pass it back to Deniece for the next step.
Well, thank you so much, James and Gautam, for this insightful exploration of integrating ApertureDB and 12 Labs to help manage video data and bring better insights for businesses. Now I'd like to turn it over for questions from everyone who joined, and we do have a couple of questions. The first question comes from Sonam, and it's how do you ensure scalability and performance when persisting large amounts of data as a graph? Are there any trade-offs?
I'm sorry, can you please repeat that again?
Yes. How do you ensure scalability and performance when persisting large amounts of data as a graph? Are there any trade-offs?
So scalability is ensured by a couple of variety of means. Like if we have like a real humongous amount of data, then we have tried with option of vertical scaling. And when it comes to improving the latency, especially like in the context of reads, just adding more instances that can serve up the requests does go a long way to cater to that requirement. Purely from the database side of things, to like improve searches in big amounts of data, large amounts of objects, we suggest people create indexes as elements, and that's a very subjective topic because it there's no one size fits all, but it depends on the access patterns on what you should build indexes for. But that goes a long way.
Thank you, Gautam. Another question from Eunice is, Is video-to-video search also possible? Find the similar videos to the input clip?
Yes, it is possible. Basically, you just put your input video through the Embed API, and then you just perform, retrieval similarity search of that of all the video of all the other video clips in your database. That's more semantically similar to your input video query. So that is basically video search.
Okay.
And another word for that is video recommendation.
And Vanessa asks, what determines the length of clip returned? What is the shortest possible length?
Yeah, so this parameter you can configure. So by default of our Embed API, we chose the length of the clip being returned to be 6 seconds, meaning that assuming you have like a 30 seconds video, you can get, if you chose the default parameters, you're gonna get 5-6 seconds video clips, right, from that 30 seconds clip. The shortest possible length is 2 seconds. So you can basically configure the parameters to 2, and then you can get like 15 embeddings out of that 30-second clips. Yeah, and the max, I think the longest possible length is 10 seconds. So yeah, I think like it really depends on your choice, the video itself, and you can experiment with like whatever length that gives the best result.
Another question is around the overhead size in ApertureDB. Is there overhead in size introduced by ApertureDB? Will my video be altered or re-encoded?
So I think the answer to that would be the graphs overhead would be negligible considering the size of the video files. Even images, I would say the size overhead would be nothing that should worry. It'd be less than 1%, maybe. I don't know the exact numbers. Furthermore, the video, when you add to the database, is not re-encoded. Whatever those operations that we did happened on the fly when we were querying. The video that is uploaded to the DB is untouched, and it can be retrieved also the same way if you do not specify any of the operations or clippings on it.
So, and there was a question about the limit to the video length, and the question is there a limit to the video length that can be processed using Marengo 2.7 put in ApertureDB? And James answered this question by saying that Marengo 2.7 can accept up to 2 hours of video length.
I should add here that at this point of time, ApertureDB does impose a limit on the video, but we're trying to bump that up. For now, we can have a 256 MB video, roughly about that size, being added to the DB, but it's like up to be bumped up to about 4 GB. We haven't tested and released that option yet, but we're on the way and making progress to do that.
So I'll wait a few seconds to see if there are any more questions. Well, if there are no more questions, we have come to the end of our Lunch and Learn, and you have given you back a few minutes of your time. You can expect to get a follow-up with the on-demand link as well as resources. And here are some of the resources link. Once again, thank you so much for joining us today. And we did have one last question. Does Marengo, it's from Vanessa, does Marengo work better with keyword or natural language search? Is it comparable?
That'd be better for natural language search. It's a model. It's a foundational model optimized for semantic understanding. So yeah, like natural language search, you can type in full query, like someone doing action, right? For instance, like a full sentences, and the model will be able to retrieve that exact segment that corresponded to those to your query. Keyword search, I think it's better for like the metadata and well, actually, I think like we actually also do pretty well with small object. So when I say keyword search, it can mean like if you want to find small object, find great details, the model can also do pretty good. But overall, from testing the model, I think the more details and context that the user problem are, I think the better the model will be to extract those information. And I think the ideal workflow is that combine both semantic and keyword search, right? So it touched on the idea about hybrid search that I emphasized earlier. Yeah, so I think, and I believe Aperture can enable keyword search as well. So that should be an ideal workflow.
Awesome. Thank you so much, James. Okay, so if there are no more questions, once again, thank you so much for attending our webinar, Building a Video Semantic Search Engine. I'll give you back some time in your day. Have a wonderful day. And on behalf of both 12 Labs and ApertureDB, we thank you for joining us. Have a wonderful day.
Thanks, guys.